Hello. So this with presentation is a discussion about the integrals of hyperbolic functions. Hyperbolic functions, in a way, or the integral of hyperbolic functions is similar to those of the trigo function. The only difference is this is hyperbolic, that is a trigo function. But most of the functions are similar. Okay? In finding the integral of hyperbolic functions, so we have to consider the 10 basic integrals of hyperbolic functions. And from there, as long as the integrand resemble any of those 10, then we just simply use the formula or the integral intended for that given integrand. But then, if it is something or at an integrand which is not the same as those 10 integrals, then that's the time that we use identities. Okay, so for hyperbolic functions. And there are also cases that we can still use, okay, the previous method. So wherein we could have hyperbolic functions. So for natural logarithm or natural logarithm involving hyperbolic functions, or exponential functions involving hyperbolic functions. So even power rule, okay, so involving hyperbolic functions. So we can do those as well. So let's try to recall some of the identities. Okay, so identities for hyperbolic functions. As you can see here, all of the 6 identities for trigo function is the same as the identity for hyperbolic function. It's exactly the same, or at least it has a resemblance, because this is still hyperbolic function. And then, in addition to that, the hyperbolic functions can be related to Euler function. So e raised to x minus e raised to negative x over 2 is the same as hyperbolic sine of x. And then the sum, if it is e raised to x plus e raised to negative x over 2, that is for hyperbolic cosine of x. And since hyperbolic sine and hyperbolic cosine are related to the Euler function, we can transform the hyperbolic tangent as well when it involves the Euler function. Okay? So by just simply changing the hyperbolic sine x over hyperbolic cosine x with that of the identity. So it's still the same. And then for the Pythagorean identity, so the difference this time is this one. If it is a difference of hyperbolic cosine squared minus hyperbolic sine of squared, so that is equal to 1. Okay, so for the trigo, that will be positive. But for hyperbolic function, so that would be minus. So therefore, so for the tangent as well as for the cotangent, it follows as well. For the double angle, it's the same as that of the trigo. But for double angle for hyperbolic cosine, it's different. Okay, so it's positive. So this is the equivalent for 1 in trigo. But for hyperbolic, so if it is plus, then that would be a double angle for hyperbolic cosine. And of course, so this one was just derived, or these two, so were just derived from here. So those are the hyperbolic identities, so involving Pythagorean formula. Now we have to recall as well the rules of differentiation for hyperbolic functions. It's the same as with the trigo. The difference is the sign. So this time, everything or all of the basic, the sine, the cosine, and the tangent, so it has a positive derivative. So that's the inverse of sine, so which is cosecant, inverse of cosine, which is secant, and inverse of tangent, which is cotangent. So once we derive them, so the resulting derivative will be negative. Okay? So negative, negative, negative. And these are the first 6 among the 10 hyperbolic function integrals. So these are common. So sine, cosine, and then secant squared and cosecant squared, product of secant and tangent, cosecant and cotangent, hyperbolic. Uh, so it's the same as long as the result, okay, so would be the inverse of the 3, the cosine, sine, and tangent, and then that makes it negative. So negative for cotangent, for negative secant, and for cosecant. So those are the first 3. The other 4, so would be the direct integral of tangent, cotangent, secant, and cosecant. So for tangent, so this time it is positive ln of hyperbolic cosine x. So since the derivative of cosine, it's this time, so for hyperbolic cosine, it's positive hyperbolic sine. So that makes it positive. But for the trigo, that is negative. We want to make it negative, so that would become negative ln secant hyperbolic secant of x. So for cotangent, it's the same as with that of the trigo. So which is ln hyperbolic sine of x. And for hyperbolic secant, so this is the same method. So in finding the solution or the integral of secant hyperbolic secant of x. So this times I can multiply this one by cosine, hyperbolic cosine of x. So since secant is the same as 1 over hyperbolic cosine of x, and this would become hyperbolic cosine of x over cosine or hyperbolic cosine squared of x dx. But then, so we have the identity for hyperbolic cosine squared x, so which is 1 plus hyperbolic sine squared x dx. So as you can see here, so our u squared is hyperbolic sine squared x. Our u is hyperbolic sine, so its derivative is hyperbolic cosine. So thus, so this is arc sine. Okay, so arc sine of u over a. Our u is hyperbolic sine, and then our a is 1. So thus, so the integral of this, so would be the arc tangent of hyperbolic sine of x. And for cosecant, hyperbolic cosecant x, so we multiply hyperbolic cotangent x minus hyperbolic cosecant of x. So in here, my assumption so would be, this would be ln. So u is hyperbolic cotangent x minus hyperbolic cosecant of x. So our du so would be, this is negative cosecant squared or hyperbolic cosecant squared x. Then minus, so cosecant is negative hyperbolic cosecant x hyperbolic cotangent x. Then all of that so would be multiplied it with dx. So once we multiply that, so that makes it so positive. Okay, so hyperbolic cosine x hyperbolic cotangent x, and then minus hyperbolic cosecant squared x. So all of this multiplied with dx. So which is, once we distribute this one, okay, and then we distribute it to negative cosecant squared, so that would become u. Okay, so that makes it du over u, or just simply this one. So ln cotangent, hyperbolic cotangent x minus hyperbolic cosecant x. So let's proceed with our examples. So for our first example, so this is a direct application of the integral of hyperbolic cosine. So we're in the integral of hyperbolic cosine is hyperbolic sine. But then, so we just have to let our u, so to be 4x, and then our du, so will be 4 dx. So dividing both sides by 4, so thus our neutralizing factor is equals to 1/4. So from here, so we can write that the answer would be 1/4, and then the integral of hyperbolic cosine is hyperbolic sine of 4x, and then that would be plus c. So that's a direct application of integral of hyperbolic cosine. So number 2, so it's a product of cosecant, hyperbolic cosecant, and a hyperbolic cotangent. So looking at the 10 basic integral of hyperbolic function, so this is one among the 10. So there is a direct integral for the product of hyperbolic cosecant and hyperbolic cotangent. So which is the negative hyperbolic cosecant of u. But then in this case, so we need to identify our u. So since our u here is 1/2 x, so our du so would be 1/2 dx. And then multiplying both sides by 2, so we'll have 2 du, so will be equal to just dx. So from here, so we could have a neutralizing factor, so which is 2. So that's our answer would be 2, the neutralizing factor. And then the integral of cosecant, so it would be negative hyperbolic cosecant, then 1/2 x plus c. And that would be the integral of the given. So next, number 3. So we have hyperbolic secant squared. So multiply it with x. So in here, so hyperbolic secant has a direct integral. Hyperbolic secant has a direct integral. And that is tangent. Okay, hyperbolic tangent. Since there's a direct integral, so our u here so would be the angle, so which is x squared. So our du so would be 2x dx. So we have x dx on the given integrand, so we divide both sides by 2, and thus x dx is the same, or would have a neutralizing factor, so which is 1/2. So this one can be rewritten as hyperbolic secant squared x squared, then multiply it with x dx. So we have x dx here, so neutralizing factor would be 1/2. So that would have 1/2, and then hyperbolic tangent of x squared plus c. So that one is our integral. Okay, so for the given. So far, so all of the 3 examples are direct application of the 10 formula. Okay, or 10 integrals for hyperbolic function. So same as true with example number 4. So we just have a product between x squared and hyperbolic secant. But then, so look at the degree. So it is x cubed. And then we could see x squared adjacent to hyperbolic secant. So most probably, okay, so our u here so is 1/3 x cubed. So our du then, so 3 times 1/3 is 1. So x squared dx. So transforming this, so hyperbolic secant of 1/3 x cubed. So that would be multiplied it with x squared dx. So we have a direct integral of hyperbolic secant, so which is arctangent, okay, of hyperbolic sine of 1/3 x cubed plus c. Okay, so examples number 1 to 4 are just direct application of the formula or 10 formulas for hyperbolic functions. So example number 5, so we have hyperbolic sine squared x dx. So looking at the given integrand, so this one does not resemble any of the 10. So in cases like that, so we need to use some identity so to find the solution. So for this one, so we can use the identity as cosine or hyperbolic cosine of 2x then minus 1. So divide it with 2 dx. So this one is taken from the Pythagorean identity for double angle. So we have hyperbolic cosine 2x, so minus 1 divided with 2. So I can distribute this one, so to become, so cosine 2x over 2. So that is the same as 1/2 the integral of hyperbolic cosine of 2x. And then minus 1/2, so the integral of dx. So we just separated this one into two terms. And then, so becoming our u here, so to be 2x, so our du would be 2 dx. So thus we have a neutralizing factor, so which is 1/2. So we already have 1/2 here, so multiply it with the neutralizing factor of 1/2. Hyperbolic cosine, so would be hyperbolic sine of 2x. And then, so minus 1/2, so integral of x or dx is just x. And then plus c. So finally, our answers will be 1/4 hyperbolic sine of 2x, so minus 1/2 x plus c. And that would be the integral for hyperbolic sine squared x dx. So using some identity. So for number 6, so we have hyperbolic secant x plus hyperbolic sine x times hyperbolic tangent x dx. Looking at the given integrand, so there is a sum, okay, so which is involved, and we can use the sum and difference rule, so wherein we can distribute the integral operation on the two terms. So we can find the hyperbolic secant x, its integral, and then plus the integral of hyperbolic sine and tangent. So for second hyperbolic secant, so there is a direct integral to that, but not for the product of the hyperbolic sine and the hyperbolic tangent. So in cases like this, okay, so we need to simplify this first. Okay, so we simplify this first. So rather than right away, so finding the integral. So to simplify this one, so since we have sine, tangent, and secant, so most probably we're just going to use the basic trigo identity, or the inverse for secant, it's the same as hyperbolic cosine x, and then plus sine, so it's on its simplest form, so hyperbolic sine of x. Then tangent is hyperbolic sine of x all over hyperbolic cosine of x dx. And then, so this is the same as 1 over cosine hx plus sine squared or sine h squared x all over cosine hx dx. So since the denominator is just the same, so we just combine. So that is 1 plus sine h squared dx. But then 1 plus sine squared h or hyperbolic sine, it's the same as hyperbolic cosine squared x over hyperbolic cosine x dx. So this will just reduce it further into just simply hyperbolic cosine of x dx. So which has a direct integral of hyperbolic sine x plus c. So this is an example where we apply first the identity, and then so once we reduce it to something that is integrable, so that's the time that we integrate it. For example number 7, so this is a rational integrand. So as I've mentioned from our previous meeting that whenever we are given a rational integrand, so we always first try the natural logarithm formula. So if we derive the denominator and we arrive to the numerator, then that makes it as integral of natural logarithm. So in this case, I'm going to let u as my denominator. So that is 1 plus hyperbolic sine squared x. And our du, so 1 is 0. And then this is chain rule, so 2 hyperbolic sine of x. So derivative of sine, so would be hyperbolic cosine of x. So which makes it, so du, so to be equivalent to hyperbolic sine of 2x. So that's a double angle formula. So dx. So that would become just simply du over u, and which is ln u plus c. Our u is 1 plus hyperbolic sine squared x plus c, or just simply 1 plus sine, so that is hyperbolic cosine squared x plus c. And that's another example. So this time, so using hyperbolic or using natural logarithm. For number 8, so we have hyperbolic secant x times hyperbolic tangent x dx, so divided with 4 minus, or square root of 4 minus hyperbolic secant squared x. So from here, so I am seeing a radical sign or radicals at the denominator. So I'm assuming that this would be integration by inverse trigo. So wherein our u squared is hyperbolic secant squared. So our u is hyperbolic secant x. And our du, so would be negative hyperbolic secant x and hyperbolic tangent x dx. So which is the same as the numerator except for the negative, or that is negative du. So divide it with, so I'll have a squared to be 4 and then a, so to be 2. So dash will have 4, so which is a squared minus u squared. So which makes it, so negative, this is arc sign. So arc sine u all over a hyperbolic sine x all over 2. So that is negative arc sine of hyperbolic secant x. So divide it with 2 plus c. So that is our 8th example. So this time, so using or involving integrals leading to inverse trigo function. So the other one, so that's natural logarithm. So this one, inverse trigo. So for number 9, so I can see 4 minus hyperbolic secant x raised to 3. So divide it with hyperbolic cosine and then cotangent. So whenever we are given this form, okay, so we're in a given function is raised to a certain exponent, so then we can use power rule. Then our u then so will be 4 minus hyperbolic secant x. So derivatives of 4 will be 0. Then negative. So secant so would be negative as well. So negative hyperbolic secant of x, multiply it with tangent hyperbolic x dx. So which makes it positive. But then our secant is the same 1 over cosine hx, and then our tangent is sine, or just simply the inverse, which is 1 over cotangent hx dx. And as you can see here, so this one is the same as this. So once we transform that, so that is similar to, so 4 minus secant, that is u cubed, and then we have dx over cosine and cotangent, so that makes it du. And thus this would be u raised to 4 divided with 4 plus c, or 1/4. Our u is 4 minus hyperbolic secant of x raised to 4 plus c. So 1/4, then 4 minus, okay, raised to 4 plus c. And that makes the example so for hyperbolic functions. As long as we know at least the 10 formula. Okay, so in finding the integral of hyperbolic function, so it will do. But then recall that our first step, okay, or the first thing to consider whenever we are given a certain integrand, so we have to classify so whether the integrand resembles any of the 10 trigo function formula or hyperbolic function formula. But then if it does not resemble any of the 10, so then that's the time that we use some identities until it will resemble any of the 10. So if everything fails, then most probably there's another way on how to do it. So we can use the previous method, so just like the natural logarithm, so we can use the exponential function, okay, so we can use even power rule. So that is our discussion, okay, so for hyperbolic function. And that will be all. Good day and God bless always.